Good afternoon, everyone. I'm glad you all made it today. Today we have David Mandrus. He is faculty at the University of Knoxville at the Department of Material Science, and he also has a joint appointment with the physics department at and at Oak Ridge National Lab, right?
Yeah, mostly right. It's an adjunct appointment in physics.
Oh, okay. Yeah, almost right. He received his PhD from Stony Brook University some time ago, and yeah, some time ago. And then afterwards, he was postdoc at Los Alamos National Lab. And while he was in Los Alamos National Lab, he got interested in the discovery and growth of new materials. Before that, he was working on infrared spectroscopy of high temperature conductors. I guess those were two grades, right? Right. And in 2000, he came to be a staff member at Oak Ridge National Lab, and since then he is
95. 2008, I started the
that's
group.
the group, right? The
Started the group in 2000.
Yeah, 2000. And he is in that area since then.
Yeah.
And since that time, he worked on many different quantum material, high temperature superconductors that I mentioned, cuprates, nucleotides, and strongly correlated superconductors, heavy fermion superconductors, strongly correlated materials, and many others. And today we will hear about how to discover new materials, right?
Okay, I hope this works. Well, sorry, I'm a little bit hoarse. I had a cold about 2 weeks ago. It's kind of lingering in the chest. But I don't think I'm contagious. You get rid of that, I expect to click OK. Yeah, let's close the PowerPoint. The slides aren't advancing anyway. Can you close it? They could maybe.
I forgot to mention that David was named one of the top investigators of quantum materials by Golden Lake Foundation, and that's the emergent phenomenon in quantum systems. And there are only a handful of those named investigators. I think ethics are the investigators.
All right. There. Start there, please. No, we can't. Yeah, literally. Yeah, this Zoom is so complicated. Here, that's it. Okay, advance, even advance. All right. You did it. You conquered the audio visual. All right. Well, thanks for coming, everybody. I've enjoyed my visit. It's my first time here at Rolla, and I've been having a good time. Nice seeing everybody. Nice seeing you. Nice seeing you for a while. All right, so I'm going to talk today about what I call the search for new materials. Now, so if you look at what drives science, especially materials physics, you can identify three major thrusts. Like new theoretical ideas are major thrusts. Something like, how topology became introduced in material science. New experimental probes like STM are hugely influential. And new materials also drive science forward quite a bit. And so I chose to work on the new materials. And during my career, at least 4 Nobel Prizes were awarded for new materials. And you can see, especially if you've been working in the area, how much these have changed physics. So in 1987, this is when I started grad school, high temperature superconductivity was discovered. And huge numbers of people started working in ITC superconductors. A few years later, fullerenes were big. Fullerenes stayed big for a long time. And then 2010, graphene was discovered. Now, one of the nice things about graphene is that it's really easy to get into the game. All you need is Scotch tape. With some Scotch tape, you can make graphene. Scotch tape on a microscope. There's even a Scotch tape dispenser in the Nobel Museum. And in 2014, this blue light emitting diode. So the person who discovered how to grow the material in the color ice. And obviously blue, you need blue to make white LEDs. So that was really important. All right. So what is a new material? So our definition in materials physics is quite loose. So a new combination of elements would be the structure. Now, some people would just call this a new compound rather than a new material. A lot of other people will just say it's a new material, but you'll hear both in use. A known material in which a new property has recently been discovered. A good example is MgB2. This superconductivity was discovered. When was it discovered? 2004. Did you work on one?
No, I didn't, but
Okay.
Julia
Okay.
Video was actually the one who calculated the bend structure of those and was presented in the same one meeting when they were presenting.
Oh, really?
Yeah.
Okay, fantastic. But it wasn't that long ago. But MgB2 was known forever. Superconductivity was discovered at 40 Kelvin, even though it was a very well-known compound, but it was new for our purposes. So another example is a known material which can be chemically built to produce a new material. These manganites, these were heavily studied over the last 20 years, but they were discovered much, much earlier, sort of in the 40s and 50s. And another, and the nanomaterial like graphene, right? That graphite is from forever. Graphene is just a new way of preparing it. So that can also be a new material. And lastly, the surface of a crystal can also be often be described as a new material, like the topological insulator, for example, just a surface state. So why would anybody want to make new materials for a living? Good question. One reason that's really appealing to me is it allows you to be problem-driven rather than technique-driven. In this respect, it's very similar to theory. A theorist can often work on a problem rather than a technique. Although even theorists have their bag of tricks, right? Theorists have their bag of tricks. They do their tricks on whatever material they're working on. But a lot of experimental techniques, in other words, if you measure, let's say you're doing photo emission, you measure a sample, and then you wait for the next sample to do your photo emission. So you have to switch from sample to sample, and problem to problem. You can be very creative. You can have an idea on Monday, and by Thursday, you know it didn't work.
Or a couple of weeks later.
But it can be very quick. You have an idea, you try it, see if it works. This follows along with nearly instant gratification. No, you don't have to bake out your apparatus for a month or whatever. I never liked baking. Probably knows about baking. And it's just plain fun. So most of us have gone into science because it's fun and making materials is a lot. So here's something called a materials pyramid. So this is, you might see this occasionally mentioned. So this was created in 2003 at Iowa State. There was a meeting at Iowa State. I think Paul organized it. And the idea was to try to get more money for the Department of Energy and focus on material science. So we had a meeting, we wrote a report, and then everybody ignored the report. I don't know if you're going to find it online, but during that meeting, Brian, who's at Oak Ridge, who's my colleague at Oak Ridge, he came up with this materials pyramid. He said, they used to have a food pyramid. A lot of the younger people probably don't remember the food pyramid. But Brian said, like, he liked to eat, so he came up with the materials pyramid. And so the idea is that the base of the pyramid, so the width of the pyramid describes the number of materials. And the height of the pyramid describes how much we know about the materials. So there's this huge number of materials at the bottom, where we know they exist, but that's about all we know about them. We don't know their properties. We don't know much of anything. So again, some people would call these compounds. And I'll mention it later. Why I'm drawing a distinction. But so as the materials move up the pyramid, more and more specialized experiments get done, and we know more about them. And also the quality of the samples needs to be higher. When your silicon wafers obviously need to be extremely high quality, very low impurities. And eventually the most studied experimental materials are useful to society. But this is a good conceptual way of thinking about sort of the universe of materials. So another very important concept that we have. So we talk a lot to theorists, and theorists have all these proposals for new ground states, new states of matter. And we kind of take it on faith that if these things are permitted, if these new states of matter are permitted by physics, then it exists and we can find it. Okay, that's kind of an article of faith that we have. So I've been doing this, I don't know, about 30, maybe more. Like this slide is a few years old. So maybe I've known it since maybe 33 years or something. I've been doing this a while. So a long time ago, we really didn't get much help. We were on our own. So we were just trying to find stuff that was interesting. Our working philosophy was basically this. The peasant who wants to harvest in his lifetime cannot wait for the initial theory of weather. And so what we did is we kind of used a combination of chemical intuition, heuristics. Heuristics are just rules of thumb, and especially structure property relationships. Those are very important for finding things. And nowadays, things have changed. So there are lots and lots of theoretical predictions, tons of them. And, but at least until recently, and maybe things are getting better, I'm not 100% sure. But most of the predicted materials are not growable. So the theorist can write a paper and predict a material, but there's no thermodynamic pathway to get to the material. So it can't be grown. And there's a lot of materials that were predicted like this. Now, I don't want to be too hard on theory because theory can be very helpful in some circumstances. And a good example where density functional theory was very useful is if you start with a known material and you have to tune it to something interesting, it can be very helpful. And so here's one of the sort of parent compounds for the Nictide superconductors, barium, iron 2, arsenic 2. And it was known to order magnetically, but it wasn't known to superconduct. And during this time, in 2008, shortly after the discovery of these superconductors, and there was an international race on to see who could find these materials the fastest. And David Singh, who was at Mizzou, I think he retired. He was at Oak Ridge and he moved to Mizzou. And so he helped us quickly find out that cobalt would be a good thing to try. And so in that case, it was extremely helpful because there's lots of possibilities for doping. And the DFT identified cobalt as a good dopant. And so in 2016, we had what's called a BRN workshop. And this is a DOE term. BRN stands for Basic Research Needs. Basic research needs for synthesis science. And one of the main conclusions of this workshop, this is 2016, was that exploratory synthesis will continue to provide the overwhelming majority of new materials for years and perhaps decades to come. Now, things have changed in the past few years. So this came out last fall, okay? So artificial intelligence, there's teams at Google and also Microsoft who are putting enormous resources into using artificial intelligence to find new materials. So Google claims to have discovered 22.2 million new materials. So there was a commentary that said, no, they didn't discover new materials, they discovered new compounds. And so material has something interesting about it. That we were kind of, so they claim that a lot of these are actually able to be synthesized or synthesizable, about 400,000. We'll see. So Microsoft is also in the game. So this whole idea of using artificial intelligence to discover new materials is, there's a huge number of papers being published in this topic every day now. It's almost impossible to keep track of what everybody's doing in this area. So there's no way a university, especially a small university, can group Google and Microsoft and Sparrow at some level. It seems very hard to do. There's not only that, so there's this also in Berkeley. So they give the theorists in Berkeley so much money that they could start a robotic lab for synthesis. They had so much money for theory they couldn't spend it all. So let's start a robot lab. And so they made a robot lab. So this is their vision, right? They want to robots operate instruments and artificial intelligence makes decisions to find useful new materials. The A stands for automated or autonomous laboratory. There's a nice video about this. If you look up like A Lab, Lawrence Berkeley, you'll see a video. You want to watch the video of the robot. Robot like picks up crucibles, moves the crucible up there, puts the crucible in the furnace. Now, we've been here before.
Outside though, right?
It's just oxide, yeah. I think the robot breaks all the time. I mean, they made a video. And it's all PR, right? But at some level, so this isn't really new because the same thing has happened in drugs, right? Pharmaceutical companies have been using, they've been designing drugs for a long time. And so I don't know how many people know Nassim Taleb, but he wrote a book. He wrote a book called Fooled by Randomness. He wrote a book called Black Swan. He's sort of an economist / financial analyst / public intellectual or something. But he always looks at risk. He's interested in how humans perceive risk. And so they wrote this article in the Financial Times. So like molecular revolution was supposed to enable drug discovery to evolve from chance to rational design. Yet dwindling pipelines threaten the survival of the pharmaceutical industry. So basically, they suggest that they misunderstood how much they understood. Basically, pharmaceutical executives overestimated their ability to domesticate scientific research. So I think we have to be a little careful not to fall into that same trap. We're thinking that we can just do everything in the computer, we don't need to. And I have some stuff at the end to kind of back that up. Okay, so let me go through a couple of examples of how people think about how to find new materials. So it's not that hard to find a new compound, okay? But in that base of the pyramid, 99.99% of those materials are boring, especially to physicists. And so we want to find materials that are interesting to physicists. That's a really hard problem. If you think about it, it's not easy. And so the way we go about doing it is through these heuristics. So one of the heuristics is to try to frustrate the material in some ways. Okay. Oftentimes, if you build in frustration, you can get emergent behavior because the material will do something surprising to remove the frustration. And frustration means the inability of the system to satisfy all the conflicting demands. And it's typically illustrated with a triangle with some spins on it interacting intermagnetically. And it says like the two spins are pointing up and down, the third one doesn't know what to do. But it's a deeper concept than that, and I'll get to that. But it actually goes back in time quite a while. It goes back at least to this French philosopher, Jean Buridan, who lived near his estates, 1300 to 1358. He was a French priest. He studied under William Malacca. He enjoyed a reputation as a glamorous and mysterious figure in Paris life. He had this bad habit of sleeping with noblemen's wives. Once he had to jump into a river. He was being chased, and his students rescued him out of the river. And he had an unusual facility for attracting academic money. But he had this thought experiment. If you look it up, it's a Wikipedia article, Buridan's ass. And the idea was that if you have a perfectly rational ass here, sitting equidistant between two stacks of hay, this animal will starve because it has no rational decision to pick one or the other. And so that is essentially the very idea we want to do with frustration. And so the holy grail of frustration is something called quantum spin liquid. So quantum spin liquid is you have these very strongly interacting magnetic moments, but because they're frustrated, they don't order. They don't order them to very low temperatures. And all kinds of interesting properties. And this is where I go back to these. You have to take it on faith. Because a lot of these models have been solved by theorists with all these very exotic quasi-particles, new states of matter are supposed to be arising from quantum spin liquids. But they're very, very hard to find. And so here's some comments. So Leon Balance is a theorist at Santa Barbara. So these are theoretically richer than the fractional quantum Hall effect. You can dope quantum spin liquids and make your path to new superconductors. And there's also a path to topologically protected quantum computing through quantum spin liquids. And there's the various types of lattices that have been proposed to realize quantum spin liquids. And so here's some of the predictions. Here's some of the exotic quasi-particles. So these are out there. You take, if you take it on faith that these theories, these predictions are real. These are all waiting discovery. So one interesting example is this magnetic monopole. So this was discovered in a pyrotor material. So if you look at, so this is called spin ice. And if you look at these moments, these are magnetic moments. So there's two pointing in and two pointing out, two in, two out. And ice does something similar. Water ice, the protons, you have two in, two out protons. So they made an analogy with ice. And it happens so if one of the elementary excitations, if you flip one of these spins, so this spin is flipped, right? So these two have basically different magnetic charges now. And then these can move, these can separate. And it turns out that mathematically, this is identical to a magnetic monopole. And in this case, this crystal, this spin ice crystal could be considered a vacuum state at some level, where you could have a monopole arising out of the vacuum. So another example of a frustrated material leading to something interesting involves these materials called Kitaev materials. So Alexei Kitaev was a theorist at Caltech. And he wrote a paper where he solved the model Hamiltonian. And this Hamiltonian turned out to be extremely interesting. His motivation was for topological quantum computation. We solved this exactly, this simple, so it's not that simple. And it's called the Kitaev model. And it involves they're called bond-dependent Ising interactions. So these are frustrated from the exchange, and it's on a honeycomb lattice. And at this point, this is just a toy model. And he predicts fractionalized spin excitations, and that they had minor fermions as quasi-particles. Okay, so he makes a toy model. The toy model predicts sort of Majorana's, itinerant Majorana's, and various other exotic properties. Okay, so nobody did anything for a while. And then a big breakthrough came where a couple of other theorists found a pathway to realizing this Kitaev Hamiltonian in real material. And the proposal was that you have edge sharing octahedron in a honeycomb J effective 1/2 not insulator. And that leads to bond directional Kitaev-like exchange. Essentially, all the other terms in the exchange Hamiltonian will cancel out and leave just that Kitaev term. And so this J effective 1/2 essentially is essentially in the strong crystal field limit, you can get this. So you have a very strong crystal field and various splittings due to crystal field spin orbit coupling and so forth. And this J effective J equals 1/2 minus layer can be realized by these ions right here, medium, ruthenium, osmium, rhodium, lithium. And so at that point, there was a global search to try to find these materials. And the first one discovered was sodium 2 iridium 03. And there was indeed evidence for this bond direction of Kitaev exchange. So that got people even more excited. And by looking at the bond lengths and so forth, people said, okay, if we could replace sodium by lithium, we could even move closer to the Kitaev model. And they did, and it did get closer a little bit to the Kitaev model. So they made this other material, alpha lithium 2 iridium 03. It's isostructural to the sodium 2 iridium 03. But there are problems with it. It's difficult to grow big crystals. The way you want to study these materials is with neutron scattering. Iridium is not a very friendly element for neutron scattering. And so the next iteration of this was, we can go even smaller than lithium, we can use hydrogen. And they did. They put, so this guy named Hideo Takagi, who's in Germany now, he was able to replace lithium with hydrogen, and it formed a pretty good spin with the caveat that this is a very disordered material. So it's a disordered, so because it's disordered, a lot of people don't really love it, right? Because the problem with disordered materials is that the neutron scattering on the disordered material can mimic a lot of the characteristics of the spin liquid. And this has continued to go on with ion exchange and reactions. We replace things like lithium with silver, or lithium gets replaced with copper. And again, you make disordered quantum spin liquids. So those are not that attractive. And so people started moving away from iridium, and one of the ones they considered was ruthenium trichloride, and we worked a lot on this. So ruthenium trichloride is quasi 2D, so layered material, honeycomb lattice, J effective 1/2 minus later. And we did a lot of neutron scattering. We learned to grow big crystals, and we did tons of experiments. And it took us like a year to get these referees. We understood what we were seeing. But we finally, we had a big PR breakthrough, and we actually made it to Discover magazine. Which never happened to me before. But from observing these Majorana fermions, one spin liquid. And this story continues. So A group out of Japan measured something called the quantized thermal quantum Hall conductance. So essentially, when you apply a magnetic field to ruthenium trichloride, you can suppress the magnetism. And then there's this region here in red, where it's believed to form some sort of a spin liquid. People are arguing what kind of spin liquid it is. And this group claims that in this region in red, they observe a quantized thermal conductance, thermal Hall conductance. And that's been a very controversial result. And there's been probably 10 or 15 papers now arguing about this back and forth. These are very difficult experiments. So another example of a way to try to find something interesting involves making materials highly pure. If you ever get a chance to read this book called Crystal Fire, it's a book about the discovery of the transistor. It reads like a mystery novel. It's a real page turner, very well written. But in here it explains that it's really, the purification of silicon is a critical accomplishment, because dirty silicon doesn't do a good job. Original ones are germanium, I think, but so the guy that learned to purify it, so Shockley was like the team leader, right? And this all happened at Bell Laboratories. So the guy who learned to purify silicon, his name was Stan. I think it's PFA, and then he discovered this technique called zone refining, where basically you have a molten region and you pass it through the sample, you can sweep out the impurities. But Shockley didn't want anything to do with that. He told Dan to work on something else. And Dan set up a system in the closet somewhere where Shockley didn't see it. And so he basically defied the boss's orders, but actually made a huge accomplishment. And so a perfect example of why making a material very pure can be seen in the fractional quantum Hall effect. And this plot is from this report from the NRC called Frontiers in Crystalline Matter. And so this mu here is something called mobility. It's basically a measure of how fast the electrons can be accelerated, or how much they can be accelerated. And so the higher mobility, the purer the sample gives you higher mobility. And you can see that with very high mobility samples, all of these features are predictable from first principles theory. Okay, so all these features are real and predictable. And this is the fractional quantum Hall effect right here. And here's a guy, his name is Warren Pfeiffer. He spent his whole career learning higher and higher purity samples of this. These are 2D electron gases. And so there's a great video. If you look up Warren Pfeiffer on YouTube, you can find this video. It explains what he uses in the machine. And he spent the last 40 years or something learning to grow better and better. And every time he makes the samples more pure, he discovers new physics. Okay, here's another example of materials that these are very popular right now. They're called kagami metals. So kagami is a Japanese word, and this is a kagami basket. And so the lattice basically these corner sharing triangles. You can see the corner sharing triangles in the basket. And so the idea is to make materials of this lattice. And so the reason we're interested in kagami metals is that these materials are great systems to combine topology and strong correlations to find new physics. Right? So the original topological materials, topological insulators, are not strongly correlated. They're completely predictable from one electron theory. These are much more interesting much more surprising and more likely. And one thing that surprised me a lot. So here's the simple type bonding calculation of the band structure of the cadmium lattice. And what you can see here, there's three features. Because this is called a direct point. This is called a Van Hoff singularity. Right here, the end point. And this blue band here is called a flat band. And that comes from destructive interference wave functions. And what absolutely blew me away is that in real materials, this simple band structure survives to some extent. There's other bands in play, and you get other bands, but you can pick out these features in the band structure. And so that physics is surviving in real materials. So they're good systems, combine topology and strong correlations. A lot of the materials have rich phase diagrams and competing phases. And there's been a lot of back and forth about whether there's time reversal symmetries broken in what's called the charge density wave state. And so the system that was studied the most of these 1 through 5 materials, where A is potassium, rubidium, cesium. And so they show superconductivity and charge density waves, two different kinds of charge density waves, and very complex phase diagrams. And so we've been studying a different class of materials, which are related, but we kind of had a mini hit with this one. This is a double layer cadmium, and we discovered a charge density wave in it, and so that got quite a bit of attention. And we're also working on some magnetic materials that have very complex phase diagrams under magnetic field. But that's the thinking. That's why we started working in this area. So I'm almost done. I wanted to leave everybody with this idea here. So here's the material. This is manganese bismuth telluride. Okay, so these are intrinsic magnetic topological insulators. So they're both magnetic and have a topological insulating phase. And one of Melina's lab mates, I guess did you overlap with me?
Yes, 1 year.
One of Melina's lab mates, Nini, who's now a professor at UCLA. She made an interesting discovery, and she learned how to grow crystals, but it really involved 1 degree. She had to calibrate her furnace to 1 degree. So you're generally working at 700 or 800 degrees, and with thermocouples. And so usually if you can get it to within 20 to 30 degrees, you're doing well. But she figured out that to get the right phase, she really had to choose what's called the spinal dwelling temperature within 1 degree of some critical temperature. And so whenever you think that AI is going to take over the world, think about this. There's absolutely no possible way that the Google deep brain is going to come up with this 1 degree dwelling temperature. It's just not going to happen. And so that's where I'm going to leave it. Thank you.
Waiting for this very nice talk, so we don't plan to find for questions.
I'm sorry I'm so hoarse. I usually don't sing this bad. I'm sure. I sound like RFK Jr. here. I don't have a problem with my throat. They're just recovering from it.
So, questions from students first, please.
So how many people are making materials here? You don't believe this. Anybody else? You're making materials? Not too many, right? Okay. So how many people are measuring materials? Probably a lot more. Whenever you do the measure, think about where they came from. Who discovered them? And why are we letting a lot of materials are discovered by chemists? So why are we letting chemists discover all our materials that we don't understand?
Yes.
It's a general question, like when you say material versus compounds.
This is something Ramsey studied. He made this distinction. So he wrote a critical article on the Google deep mining paper. And he wrote this distinction. I can send it to you if you like. He wrote it like a commentary where he draws a distinction between material and compound.
So to me, it seems like when you have a established structure type and you're kind of substituting with different elements, you're making probably compounds of that particular series, right?
Sure. I don't make that distinction, but other people, I know Rand does. So I wanted to mention, do you make that distinction?
I don't know, to me, if it's a new structure type, cryptographically, and then I kind of try to call it a new structure, crystal structure.
New structure.
Yeah, rather than as a derivative of some other
Yeah.
structure type where I did some substitution with.
Yeah, I think Rand's point was that the Google found, 2 million boring things. Whereas the material applies to that people are interested in for some reason. Whereas the compound may not necessarily be that interesting, just the compound. Again, I don't know, not that many people can draw that distinction, but in this biting commentary, he draws that distinction.
Also, in one of your slides, there's discovery term. So is it discovery of compound or it's invention? Discovery seems to be that something is sitting there, nobody has gone there to find it.
That's exactly what you discovered in material.
So they all exist. It's something.
That's a good question, actually. I haven't thought deeply about it. But yeah, I guess I've always just thought about it as it's out there to be discovered, but I guess you could look at it differently. Right? I mean, I heard I heard a podcast about a lady who she's at the University of Arizona. She has this institute for this. She's working on the origins of life. Talk about big questions, right? She's able to get money for working on the origins of life. But she's actually developed some interesting new ideas that go to the point. And basically, she's wondering, well, how can we tell? Let's say we see a planet, and we want to know whether there's any life on that planet. If you do this spectroscopy, you can see what kind of compounds are on there. And there's different levels of complexity. And she talks about this idea, it's called assembly theory. And the way it works is that if you're just random, you're not going to get very many complex molecules. You may get a few, but not many. Whereas if life is involved, you start getting more complex molecules. And it's kind of similar to what you're saying, right? It's not going to just happen. We have to go and do it. Right? These materials aren't going to create themselves. It's not like we're discovering a continent. They're already there. We have to go and do it. So in that sense, it's an invention. You can say that it's there if you do it. I don't know.
Any further questions?
This goes back to the very beginning, where you mentioned that a lot of the things that the theorists come up with, can't make thermodynamically. Now, could you, and I understand this is completely impractical, but could you make them with like optical tweezers, one atom at a time, or would they simply never end up in the structure that you want?
That's an interesting question. So where's that DFT? Who's the DFT to this? They're stable in DFT, right? Density functional theory. So the question, you probably couldn't make them one out of that. That'd be my guess. I think if you could put them together, they would stay together. And the problem, okay, I'll tell you the reason why. So theorists can calculate whether things are stable or not. But it takes work. You have to calculate something called the convex hull, which essentially is a surface of stability. And then you have to calculate where your material is compared to this surface called the convex hull. And if it's close to the convex hull, it can probably be made. If it gets far away from the convex hull, other things are going to be made first. And it can't be. But it's expensive. You have to do a lot of calculations. And I just don't think, that you can just publish the paper and not do all this other work, or you do all the other work, publish the paper, and get the same, it doesn't give you any benefit, but it's a lot more work. So I think there's incentives just to publish materials that can't be grown.
Also on top of that, a lot of materials are industrial and kinetically stable, so even if you do high level of calculation, you have no clue of those materials.
Oh yeah, that's a whole nother, so yeah, we're just scratching the surface, right? All these, the ones that we talk about today are all thermodynamically stable. But there's millions of materials that are kinetically stable. So for example, and I mentioned this earlier, there's a self-state chemist named Mercury Kansas at northwestern. And he likes to show the space diagram, carbon, hydrogen, oxygen at 800 degrees C. And there's like 4 compounds on it. Whereas, all of organic chemistry is in those compounds. When you lower the temperature, you can get all these kinetically stable materials, compounds. We can do something similar. We just haven't got there yet. That's certainly a place to look.
Yeah, maybe I'm making a fool of myself now. I'm not from this field of interest at all. I'm a jurist working in quantum electrodynamics. But, don't we hear about these even lab-grown diamonds and about, these ovens that can make single crystal rubies now, large ones. Does it make sense to speculate about the use of such ovens and that operate under intense pressure in order to make, new materials with large scale single crystals out of the new compositions that don't occur in nature, like yellow sapphire that has very specific optical properties that you need for this and only this application.
Yeah, in the US, we're kind of behind in that area compared to Japan. Japan has put a lot more effort into high pressure synthesis than we have. I visited a lab in Japan at NIMS, National Institute for Material Science. They have a lab the size of a gymnasium. I was able to stand, they have a high pressure cell and I could stand up in. It's just incredible. And we have nothing like that here in the US, but absolutely you can do that. And China's putting a lot of effort into high pressure synthesis as well. And I think the main thing to think about, so, and this was brought up in a talk I saw recently. So, so a discovery is made.
Well, no, actually, between the single crystals are also grown under pressure.
Absolutely, yeah. Now, so you ask yourself, okay, so there's a scientific discovery. When does the technology happen? Right, when does that technology happens fairly quickly after the discovery. That's when the patents are made. That's when a lot of the technology is created. And so you have to be very fast with the synthesis of materials if you want to capture some of that technology. If it takes you a year to figure out how to grow something, you've lost the technology. So, a lot of, you have to have that capability ready to go.
We still have time for further questions.
I have a question. So for the lithium-based compounds, it was substituted with hydrogen.
Yes.
How was it done?
A technique called ion exchange.
So it's nothing what we do.
No, it's very similar to the soft chemistry that we were just talking about.
I'll have to tell this
It's not, yeah, it's easier, including organic acid, like benzoic acid.
something I need to look.
Yeah. I mean, it's just, it's a wet chemistry technique. That's not something. Yeah, it's. Yeah, disorder though. It's a problem. But, you know, as I was mentioning, I'm pretty hopeful. I mean, that our ability to work on small samples has improved tremendously since the discovery of graphene. And so a lot of these materials that we can grow using these soft chemistry techniques, even though they're distorted, you can find small pieces that are pretty well ordered and do good physics on those. With disorder, it's hard to do good physics on disordered samples. I mentioned that there's people working on photons here. Photons are so clean, optics is so clean compared to, you know, real materials are impurities or distorted. And a lot of times the properties are determined by these extrinsic effects. And so separating out the important intrinsic effects from the extrinsic. Yeah, sorry, I sound terrible. I really feel like I'm okay. I know how it feels.
Words in defense of the door. When you put materials together, is a different axis that is completely on the score. I would say it's a different physics. It's not that physics. The new physics comes from the complexity. The complexity is a completely different axis, which I don't see how you can explore it experimentally. The only way is to simulate it.
Just what you said just a moment ago about, you know, a disordered system, and then you find a little chunk.
Right.
That's ordered. How do you go about isolating that?
I'm not sure. I think what you could do. No, I mean, this is something I'm thinking about. I haven't actually done it yet, but I think you can go in with I guess you can start with their tweezers. You can pick out a piece. You can X-ray it. If it looks good by X-rays, you can you can pattern it with something called a focused ion beam microscope. So there's been a lot of progress in these focused ion beams. They make them using xenon atoms now. They're called plasma fibs. You can basically take a crystal that's maybe 100 microns by 100 microns, and you can shape it into almost anything you want. You can shape it into a small device. You can put it on the substrate, attach leads to it. You can do all kinds of experiments. So if you can convince yourself with X-rays that you have a good sample, then you can go and start doing electrical measurements on it. Magnetic measurements might be a little harder, but it's probably doable as well. But yeah, that's kind of, it's something I've been thinking about, but obviously it's not easy. But
With predictability would also be a problem in that case, right?
maybe it depends.
Yeah, it depends on.
It depends whether, you know.
Disorders.
Yeah, no, I think some of the crystallites are ordered and some are disordered. So, you know, if you pick out two ordered ones, they should reproduce. But I haven't done it yet, so. But, you know, might be a good thing for your next proposal.
No. That, it would be.
Somebody should do it. I'm not sure.
No.
I'm not sure.
Further question, please?
How about the students? And if our students are shy, I think question. So I'll tell you a story. So I went to Stony Brook for grad school. And we had a very famous Nobel laureate, C.N. Yang, at Stony Brook. And shortly after buckyballs were discovered, we had a colloquium speaker talking about fullerenes. And C.N. Yang asked the most elementary questions. absolutely undergraduate questions. And I thought that was really inspiring. So, don't worry that your question seems too elementary. If CNN can do it, you can do it. Yes.
So when you were referring to the spin fluid, is that like just where the spin can be aligned in any direction? Essentially?
It's fluctuating.
Okay.
It's like, if you think about a liquid or fluid, right, it's, so that spin would be jumping around. It wouldn't be going in one direction, it would be. And the other thing about the quantum spin liquids is they're highly entangled. And people are trying to devise ways of measuring the degree of entanglement. So, yeah, and it's that entanglement that causes all these weird quasi-particles that develop. And so these things have been studied heavily. The theorists love these quantum spin liquids. They're really exotic states of matter. They're so hard experimentally, very, very difficult. Maybe someday we'll find a really perfect one. I mean, the ones we find are close. They're called proximate. They're close to being quantum liquids. And we got to kind of see some of the effects.
We already see with quantum gases, right?
Quantum what?
With quantum gases, we already see spin liquids. Hi, I'm sorry.
There you go. Yes, there you go on gases.
So, any further question, final question maybe? Please.
What? Find this picture.
Oh, okay. So this was at a castle in France. So there was a guy named Roy Edelman. Edelman, he started a chemical company in California. And he invented something called the Edelman flask or something. He made a lot of money. And he endowed there's a quantum institute at UC Irvine and Caltech. That's been endowed by Edelman. And Edelman also bought a chateau in Normandy, France. And every couple of years, the people at Irvine would invite a number of people to go and visit his chateau for a week in the summer. And I was all invited there once. And so we went there. And it turns out that this chateau in France had been owned in the past by Malcolm Forbes of Forbes magazine. And Malcolm Forbes was a big balloon enthusiast. And Malcolm Forbes brought ballooning to Normandy. And it's been there ever since. And so, they had balloon museum at the chateau. And they took us up. So we went up about 100 feet. There were a bunch of us, right? So we went up a little bit. But one thing that really surprised me was that those things are really aggressive. I mean, those burners, those are huge and they're powerful. Those are not meek. They're very powerful, very intense flames. And this is Claudia Belser. So that's Claudia Belser. She was there as well. She was a Max Planck director in Germany. And one of the leaders in topological materials. So, but that was a lot of fun.
Okay, with this, we would like to thank you so much for this interesting talk.
You have any